Hi everyone, and welcome to my talk entitled An Intersectional Definition of Fairness. So this is joint work with my colleagues from the University of Maryland, Baltimore County. So this talk is about fairness in machine learning, which is the concern that AI systems can potentially exhibit unfair or discriminatory behavior, typically because biases inherent in data can lead the behavior of these machine learning algorithms to discriminate against certain populations like gender, along lines of gender or race, and so on. So if you want to learn more about this topic, I recommend the books and articles on the slide. But a couple of important motivating examples are bias in criminal justice risk assessments, which are used for bail and sentencing decisions, and bias in AI recruiting tools, which have shown bias against women. So suffice to say that AI bias and unfairness is a real problem with real world consequences, and it's affecting real people, and we urgently need to do something about it. So of course, the AI community has taken upon itself to try and address this problem, and there's been a lot of work that's been done. Most of this work can be summarized as an approach where an AI fairness definition is proposed, which tries to quantify AI or machine learning unfairness, and a learning algorithm is proposed, which tries to enforce this criteria. And we can summarize most existing AI fairness techniques as encoding a notion or a principle of fairness related to a concept called inframarginality. So inframarginality is the principle that attributes that are used by an algorithm may have different distributions which depend on the protected attributes. This is emphasized with the following typical causal assumption that is used by many inframarginal approaches to fairness. So these approaches typically assume that there are one or more protected attributes, often only one of them, such as gender or race, and the protected attributes will influence the features that are observed by the algorithm X. Now, these features are also assumed to affect the outcomes that are such as whether a person will repay a loan or whether they will succeed at a particular college. And the features also affect that individual's level of merit or risk, such as their ability to repay the loan or their ability to succeed in college. So in inframarginal approaches to fairness, in an ideal world, we will take out the impact that may be unfair of irrelevant features and consider only the merit or ability of a person in the assignment of outcomes to that person, such as a prediction that they will repay a loan, therefore they are going to be given that loan. So inframarginality emphasizes that the algorithm should perhaps legitimately behave differently for each group. So we can admit a disparity in the outcomes assigned to different genders or different races. Instead, individuals should ideally get their outcomes assigned according to their individual merit or risk, their ability to succeed at the task measured by outcome Y. And therefore, under inframarginality, an algorithm would only be biased if it is more inequitable than the data suggest. So even if there is disparity along lines of gender or race, for example, this may not be considered biased unless the algorithm is more biased than the data that it was trained on, which are supposed to be a fair measure of a fair society. So in this work, we take a different approach to AI fairness, motivated by a critical lens for thinking about fairness and unfairness in society called intersectionality, which arises from the humanities literature. So intersectionality, due to Kimberly Crenshaw and colleagues, posits that there are systems of oppression that are built into society which lead to unfair systematic advantages and disadvantages along intersecting protected dimensions like gender, race, nationality, age, and so on. So inframarginality posits different causal assumptions to inframarginal approaches to fairness. And the assumption is something like the following. So we assume that there are multiple protected attributes A, and that there are systems of oppression in society, such as racism, sexism, and the prison industrial complex or the school to prison pipeline, which cause advantages or disadvantages differing depending on the set of protected attributes, like the intersection of gender and race. So the lived experience of Black women may be different to the lived experience of white men. And so these advantages and disadvantages will affect our observed features, of course, but they will also affect our ability to succeed at a particular task, like repaying a loan or succeeding in college, which is our outcome Y. So individuals may not succeed to their potential because they are in fact impacted by these unfair processes. So you can imagine, for example, a college student who comes from a poor family and they don't have enough money to put food on the table. They have sick relatives who are unfairly disadvantaged in their access to health care. They constantly worry about, and that they are subject to racism and are constantly told that they will never succeed in this college. So that individual will not succeed to their potential, and even though they could potentially have succeeded if they were not disadvantaged in these ways. So in an ideal world, according to intersectionality, an AI system should assign a decision like admitting a person to college based on that person's potential, regardless of the disadvantages that they face. So in this causal diagram here, you will note that there's no pathway or arrow from the protected attributes A to the outcomes Y. So this would imply that, generally speaking, there should be parity in the outcomes between the protected groups for any protected group and any outcome. Of course, there may be other factors that are not measured that could confound this process. And in such cases, we would have disparity, but we can address that separately. And we do consider that in a longer version of our paper on the archive. But typically, intersectional fairness aims to rectify harmful effects of oppression, and algorithms should not generally behave differently for each group. We should have some notion of parity. So to summarize, an intersectional definition of fairness, which we'd like to propose, should have multiple protected attributes like gender and race. It should consider all of the intersecting values of the protected attributes, like we want to protect Black women and the behavior of the algorithm versus white men. And yet we also should still consider that we would like to protect women overall while still protecting Black women. Systematic differences should assumed by intersectionality due to structural oppression should be rectified even if they're in the data rather than codified by the algorithm. And we'd like to protect minority groups because these are often the groups that are subjected to the most oppression and marginalization in society, such as racism, compared to the dominant group. So in this work, we propose methods and definitions for fairness in machine learning based on an intersectional perspective. So we define intersectional fairness definitions, theoretical results about these definitions' properties, a learning algorithm to enforce our definitions, and experimental validations of our approach. So it's worth looking in the literature to see if there are existing methods that would satisfy this intersectionality criteria that we considered on the previous slide. And perhaps the best candidate is subgroup fairness, which is a fairness definition that does consider intersectional groups, but it doesn't aim to satisfy intersectionality as we have defined it. Instead, it aims to solve a problem called fairness gerrymandering, also known as subset targeting, in which an algorithm does satisfy parity across different groups, but is still unfair in terms of targeting of subgroups of those protected groups. So subgroup fairness tries to protect those subgroups, so it does handle intersectionality, but it does unfortunately punt on small groups. In other words, minority groups. And it does this by downweighting the consideration of groups according to the size of that group. And so minority groups get less consideration under subgroup fairness. And that's shown by the term circled here, which is the minority downweighting term. So we'd like a definition that handles all of the properties of intersectionality, unlike previous definitions of subgroup fairness. So in this work, we do propose such a definition, which is called differential fairness. Differential fairness is going to measure the fairness cost of both algorithms and data. And that fairness cost is going to correspond to privacy and economic guarantees, which will tell you what it buys you for a particular level of fairness of an algorithm, and gives you an interpretation of the fairness. It has nice properties that we can prove regarding intersectionality, and it's also related to a legal criterion called the 80% rule. So let's start from the 80% rule, and we'll use that to motivate our definition of fairness, and then we will show that it has good properties regarding intersectionality. So the 80% rule is a legal criterion of fairness, which is used for laws such as Title VII of the Civil Rights Act of 1964 or the Americans with Disabilities Act and other anti-discrimination laws. So because there's more than one such law, it's codified in the Code of Federal Regulations, uniform guidelines that apply to all such anti-discrimination laws. And these guidelines correspond to the 80% rule, also known as the 4/5 rule. So consider a company's hiring policies, which may correspond to different hiring or selection rates for different demographics, like men and women. So if one group, like men, has less than 4/5 the hiring rate of another group, like women, then that would be considered under the 80% rule to be evidence of adverse impact or discrimination. Whereas if that is not satisfied, then we would not see evidence of adverse impact. For example, here we have a red group and a blue group, which are two demographics, and the red group is hired 3/4 of the time, whereas the blue group is hired 100% of the time. And so a selection rate of 75% is less than 80% of a selection rate of 100%. 70.75 is less than 0.8. So in this case, there would be evidence of adverse impact under the 80% rule. So one insight in this paper is to connect the 80% rule with a fairness criteria called differential privacy. And the connection is going to be that both of these criteria, one for privacy, one for fairness, are aiming to ensure that ratios of probabilities of certain outcomes are close to 1. And in differential privacy, it tries to ensure that they are less than each of the epsilon, where epsilon is the privacy level. And in the 80% rule, it ensures that probabilities of selection rates are, for different groups, are bounded by a fixed value here, 0.8. So we're going to use that to define a similar notion of fairness to differential privacy, which is called differential fairness, and which is going to measure the fairness cost of an algorithm with an epsilon similar to differential privacy. So the scenario is in this picture. We have individuals' data. They come from a certain distribution, which we model. It's a population. There's an algorithm which is supposed to be fair, which provides outcomes Y for each individual, and each individuals have protected attributes. And we like to have privacy about those protected attributes, even given an outcome Y. So our proposed differential fairness criterion has the following definition here. Essentially, it's like the 80% rule in that it protects ratios of probabilities for outcomes, in this case, like hiring or not hiring, between protected groups, which are assumed intersectional. So similar hiring rates for Black women and white men, for example. The ratios need to be bounded by each of the epsilon, and epsilon will be the level of fairness of a particular algorithm. So due to the relationship to differential privacy, this gives us a privacy interpretation of epsilon. The upshot is, for example, if a person is given a loan, that's the outcome of the algorithm, then an adversary cannot infer that because they're given a loan, that person must be a white man. We also have a nice intersectionality property in that if you protect multiple dimensions like gender, race together, then you automatically get the same level of fairness epsilon for race by itself, or gender and nationality together. We have other theoretical guarantees like generalization guarantees from data, or economic guarantees regarding the behavior of the algorithm overall between different groups. And we can also use a variant definition where we measure the amplification of the algorithm of the bias compared to the fairness epsilon for the data. So this would be a more politically conservative definition that implements inframarginality, since it tries to penalize only the amplification of a bias by the algorithm and not correct for bias in society. So we proposed a learning algorithm which just performs gradient descent on a loss function penalized by our fairness criteria, either differential fairness or its bias amplification extension. It can be done using backpropagation and order differentiation for neural network classifiers. And we can do the same for subgroup fairness. So we found that both subgroup fairness and differential fairness classifiers will improve the fairness under both metrics, both overall and per intersectional group, as we see on the left plot. However, as we see on the right plot, the subgroup fairness classifier will ignore minority groups. It actually can make their fairness worse, and it tends to have worse behavior for minority groups. Whereas differential fairness classifier protects minority groups just as well as majority groups, and it improves things for both the subgroup fairness criterion as well as the differential fairness criterion. So that's it. Thank you. Please send me any questions.